Hi there, it's Marco from Donut Lab. You are watching our battery proof series called I Donut Believe. In this series, we demonstrate the capabilities of Donut battery, which is the world's first solid-state battery used in production vehicles.
Donut Lab says their battery delivers 400 watt-hours per kilogram. That's the number. That's the whole pitch. If it's true, it's the most important battery ever built. It would beat every production cell on the planet by a margin that should not be physically possible. But here is what happened when the numbers actually leaked. SGS Germany, an independent testing and certification company, tested a cell from CT Coding, Donut Lab's upstream technology partner. They weighed it. They measured the energy. And when you divide one by the other, you do not get 400 watt-hours per kilogram. You do not get 350. You do not even get 300. The authentic lab report puts the energy density below 268 watt-hours per kilogram. And it gets worse. A second SGS report, one that showed slightly higher numbers, topping out at 297, was officially declared by SGS Germany to be altered or fake. So the real number is below 268. The forged number is 297. And the marketing number is 400. That is not a rounding error. That is a 50% gap between what they are selling and what the lab actually measured. And the simplest test in the world, putting the battery on a scale, has never been performed by VTT, the lab they hired to validate their claims. In this video, I am going to walk you through the math. Step by step. No jargon, just arithmetic. And by the end, you will understand exactly why battery engineers are calling this impossible.
Donut Lab just released their third-party validation test for their solid-state battery. And while not as big of a bombshell as their second, this one still has some pretty deep insight. Plus, we have 3 tests now, so there's a lot of numbers and we dug into it. They tested self-discharge. Not what I was hoping for. I really wanted to see a cold weather test, but they did self-discharge.
What energy density actually means. Before we get into the numbers, I need to explain one concept. Just one. And everything else in this video will make sense. Energy density is a ratio. It is the amount of energy a battery stores divided by how much it weighs. That is it. Watt-hours divided by kilograms. More energy and less weight equals higher density. Think of it like a backpack. If you can carry 50 pounds of supplies in a 10-pound backpack, that is a 5-to-1 ratio. If someone claims they can carry 50 pounds in a 5-pound backpack, that is twice as good. But if you weigh the backpack and it is actually 12 pounds, they lied about the ratio. The supplies did not change. The backpack is just heavier than they said. That is exactly what happened here. We know how much energy the Donut Lab cell stores, VTT measured that. We know how much the cell weighs, SGS measured that. And when you divide one by the other, the ratio does not match the marketing. So let's do the math. VTT tested the Donut Lab cell and measured approximately 26 amp-hours of capacity at roughly 4 volts. Multiply those together and you get about 104 watt-hours of total energy per cell. That is the numerator, the energy. Now for the denominator, the weight. And this is where it gets interesting. Because VTT never weighed the cell. They were never asked to. They tested voltage, current, and temperature. But they never put it on a scale. Think about how strange that is. Donut Lab hired one of Europe's most respected research labs to validate their battery. They asked VTT to test charging speed. They asked them to test heat tolerance. They asked them to test self-discharge. But they did not ask them to do the one thing that would prove their headline claim. Weigh it. Weighing a battery cell takes 30 seconds and a kitchen scale. They did not do it.
400 watt-hours per kilogram of energy density. Charges in 5 minutes, lasts for 100,000 cycles, uses abundant non-toxic materials.
The weight math. Okay, here is where the numbers tell the story. Scenario 1, the marketing claim. If the Donut Lab cell truly delivers 400 watt-hours per kilogram and it holds 104 watt-hours of energy, then the cell can weigh a maximum of 260 grams. 104 divided by 400 equals 0.26 kilograms. That is 260 grams. About the weight of a large apple. Not 1 gram more. If it weighs 261 grams, it is not 400 watt-hours per kilogram anymore. The math is absolute. Scenario 2. The altered SGS report. Now let's use the best number from the altered SGS report, the one SGS Germany officially said was fake or tampered with. Even that inflated report topped out at 297 watt-hours per kilogram. Working backward, 104 watt-hours divided by 297 equals 350 grams. So even the fabricated data implies the cell weighs 350 grams, almost 100 grams heavier than what the 400 W per kilogram claim requires. Scenario 3. The authentic SGS report. The authentic SGS report, the one SGS confirmed is real, shows energy density numbers significantly below the altered document. Below 268 watt-hours per kilogram. Let's be generous and use 250. That means the cell weighs at least 416 grams. 104 divided by 250 equals 0.416 kilograms. So here is the picture. Donut Lab says 260 grams. The forged lab data implies 350 grams. The real lab data implies over 400 grams. A battery cannot shed 40% of its physical mass between the testing lab and the press conference. Mass is not a marketing variable. It is a physical constant. The motorcycle problem. And this gets worse when you apply it to the actual vehicle. The Verge TS Ultra has a 33.3 kilowatt-hour battery pack and a total vehicle weight of 235 to 250 kilograms. If the cells really deliver 400 watt-hours per kilogram, the raw cells weigh about 83 kilograms. Add 25% for the pack structure, housing, cooling, wiring, battery management system, and the full pack weighs roughly 104 kilograms. Subtract that from the 235 kilo bike and you have 131 kilograms left for the frame, wheels, brakes, suspension, radar, and a hubeless rim motor that generates 1,200 Newton meters of torque. Tight, but theoretically possible. But if the real energy density is 250 watt-hours per kilogram, the raw cells weigh 133 kilograms. The pack weighs 166 kilograms. Subtract that from 235 and you have 69 kilograms left for the entire motorcycle. 69 kilograms. That is 152 pounds. For a high-performance electric superbike with a motor powerful enough to twist steel. You cannot build that motorcycle for 69 kilograms. It is not an engineering challenge. It is a physical impossibility, so either the battery is really 400 watt-hours per kilogram, or the motorcycle's published spec sheet is fiction. Both cannot be true simultaneously.
Today we're going to talk about lithium iron phosphate batteries and what kills them, misconceptions, and how to ensure that your battery lasts for a very long time.
The voltage fingerprint. Now the weight math alone is damning. But it is circumstantial. Maybe the SGS cell was a different batch. Maybe VTT tested a newer, lighter version. There are hypothetical defenses. The discharge curve is not hypothetical. It is a forensic fingerprint. And it tells us exactly what is inside this cell. Here is how it works. When a battery discharges, its voltage does not stay flat. It changes over time in a very specific pattern, a curve. And the shape of that curve is dictated by the chemical reactions happening inside at the atomic level. Different chemistries produce different curves. Always. Without exception. It is like a voice print. You can disguise the words, but you cannot disguise the voice. The Donut Lab cell tested by VTT operates in a voltage window of 2.7 volts to 4.2 volts, with a nominal plateau at 3.6 volts. It uses a standard constant current to constant voltage charging profile with an exponential current decay at the top of the charge. These are not arbitrary numbers chosen by Donut Lab. These are the thermodynamic limits of specific molecules. And those specific molecules have a name. That voltage window, 2.7 to 4.2, nominal 3.6, is the exact, unalterable signature of a lithium nickel manganese cobalt oxide cell. NMC. The most common lithium-ion chemistry on the planet. The one in your laptop. The one in a Tesla. The one in a Porsche Taycan. Let me show you why this matters by comparing it to other chemistries. Lithium iron phosphate, LFP, operates at 3.2 volts with a very flat discharge curve. Sodium ion operates between 2.5 and 3.5 volts. Zinc ion operates below 2 volts. Aluminum ion? Below 2 volts. None of them produce a 3.6 volt plateau. None of them charge to 4.2 volts. Only NMC does. Only lithium-ion NMC does. A PhD researcher named Zeroth conducted a systematic elimination analysis for Hackaday. He tested the voltage data against every commercially viable battery chemistry. His conclusion, corroborated by multiple domain experts on engineering forums, the discharge curve is highly, if not exclusively, consistent with a standard NMC chemistry cell. Which brings us to the no-lithium problem. If the cell exhibits the exact thermodynamic voltage fingerprint of a lithium-ion NMC battery, then claiming it contains no lithium is not a marketing exaggeration. It is a contradiction of physics. You cannot generate a 3.6 volt nominal plateau from a chemistry that lacks the electrochemical potential to produce it. The voltage is not a design choice. It is an atomic constraint. When battery engineers pointed this out, Donut Lab shifted their language. They stopped saying no lithium. They started saying not lithium ion. That is a very specific linguistic pivot. In battery terminology, not lithium ion usually means lithium metal, where the anode is solid metallic lithium instead of lithium ion stored in graphite. But even if the anode is lithium metal, the 3.6 volt plateau means the cathode is almost certainly NMC, which means the cell depends on cobalt, nickel, and manganese, which directly contradicts their claim that the chemistry avoids rare earth elements and toxic materials.
The global electric vehicle market is entering a new phase in which battery chemistry, rather than vehicle design, may actually determine how quickly prices are falling.
Why no lithium cannot reach 400 watt-hours per kilogram? Let's assume, for the sake of argument, that the voltage fingerprint is wrong. Let's give Donut Lab every possible benefit of the doubt and say maybe it is some exotic new chemistry that just happens to look like NMC on the outside. Fine, let's test the no lithium claim against the laws of physics. If a battery does not use lithium, it has to use something else. There are 4 serious candidates. Let's go through each one. Sodium ion. Sodium sits right below lithium on the periodic table. Same column, similar behavior. But a sodium ion is larger and more than 3 times heavier than lithium. Heavier ions mean a heavier battery. Lower voltage means less energy per charge cycle. Current commercial sodium-ion cells top out at 160 watt-hours per kilogram. The Fraunhofer Institute projects a long-term theoretical ceiling of about 200. Sodium cannot reach 400. Zinc ion. Zinc batteries are safe and cheap because they typically use water-based electrolytes. But zinc atoms are heavy, 65 grams per mole versus lithium 7. And water limits the voltage window, which caps the energy. Best zinc ion cells today hit between 50 and 135 watt-hours per kilogram. Zinc cannot reach 400. Magnesium ion. Magnesium can carry 2 electrons per ion, which is theoretically great. But in practice, the magnesium ion's strong charge makes it sluggish inside a cathode crystal structure. Real-world full cells deliver about 68 watt-hours per kilogram. One research team claimed 560, but that was a non-rechargeable primary cell for deep-sea use, not a fast-charging EV battery. Magnesium cannot viably reach 400 in a rechargeable format. Aluminum ion. Aluminum can carry 3 electrons per ion, and it is the most abundant metal in Earth's crust. Sounds perfect. But finding cathode materials that can survive the large, highly charged aluminum ions without degrading is incredibly difficult. Practical cells hover between 60 and 150 watt-hours per kilogram. Aluminum cannot reach 400. Here is the fundamental problem. Lithium is the lightest metal on the periodic table. Atomic mass 6.94. It is also the most electropositive element, meaning it generates the highest voltage per electron of any metal. That combination of extreme lightness and extreme voltage is why every battery pushing past 300 watt-hours per kilogram uses lithium. There is no shortcut around the periodic table. Claiming 400 watt-hours per kilogram without lithium is like claiming to build the world's lightest aircraft without using aluminum, titanium, or carbon fiber. The atoms required to achieve that energy-to-weight ratio simply are not there in any other element.
If you think about 3 megawatts, normally the world has always had in mind a big container of batteries. But with supercapacitor and SGS 2.0, we can do it in just a 19-inch rack system, in the footprint slightly above a quarter of a square meter.
What about supercapacitors? Now some of you are thinking, what if it's not a battery at all? What if it's a supercapacitor? This is actually the most elegant theory that was floating around the engineering community, and I want to give it the respect it deserves before explaining why it doesn't work. Supercapacitors store energy electrostatically, on the surface of porous materials like activated carbon instead of through slow chemical reactions. And that distinction explains 2 of Donut Lab's most aggressive claims perfectly. First, supercapacitors charge almost instantly. Seconds, not minutes, because there's no chemical diffusion to wait for. That matches the 4.5-minute charge time. Second, supercapacitors survive 50,000 to 100,000 cycles easily, because there's no crystal degradation, no dendrite formation, no physical swelling. That matches the 100,000 cycle claim. Lamborghini even used a supercapacitor in the Sin hypercar, so charge speed and cycle life both check out. But the theory dies on 2 points. First, energy density. Commercial supercapacitors deliver 5 to 15 watt-hours per kilogram. The absolute theoretical maximum for carbon-based or hybrid supercapacitors is about 50 watt-hours per kilogram at the system level, not 400. Not even close. You'd need something roughly 8x beyond the theoretical ceiling to hit 400. Second, the discharge curve shape. A capacitor discharges linearly, the voltage drops in a straight line as charge depletes. The VTT data shows a flat voltage plateau at 3.6 volts followed by a sharp drop. That flat plateau is the exclusive domain of chemical batteries undergoing a phase change. Supercapacitors physically cannot produce that curve shape. It's like comparing the sound of a drum to the sound of a violin. They're both instruments, but you can tell them apart in a single note, and for what it's worth, Donut Lab's own executives have said the technology is not capacitor-based. So even the company has closed this door. VTT self-discharge test confirmed this independently. The cell retained 97.7% of its charge after 10 days of idle storage. A supercapacitor would lose most of its charge in hours to days depending on design. This is definitively a chemical battery. The question is which chemistry?
But after hearing mixed things about their future, I wasn't sure what to believe. However, I think I found the missing piece of information, a patent from battery giant CATL explaining their reinforced sodium-ion cells.
What real 400 watt-hours per kilogram looks like. So who is actually approaching 400 watt-hours per kilogram? And what does it take to get there? CATL, the world's largest battery manufacturer, has demonstrated condensed matter/high-energy prototype cells reaching up to 0.500 watt-hours per kilogram at the cell level in lab conditions. It uses a novel polymerized electrolyte with an ultra-high-energy cathode system. Chemistry direction has been publicly discussed, but it is not a mass-production automotive product. It is initially targeted at aviation and next-generation high-energy applications, not cars, not cost-optimized mass production, and not shipping in motorcycles. Factorial Energy has validated up to 375 watt-hours per kilogram with Stellantis using lithium metal anodes and solid-state electrolyte systems. 77 amp-hour pouch cells have been publicly referenced. Chemistry is patented and disclosed at a high level, with extensive OEM validation. WeLine is supplying zeroing 360 watt-hours per kilogram semi-solid state cells in NIO vehicles such as the ES6. Lithium metal and silicon-based anode architecture. Chemistry is disclosed at a system level and already deployed in production vehicles, though still limited in scale. Samsung SDI is targeting next-generation solid-state cells with volumetric energy density targets around 900 watt-hours per liter, using anode-less architectures where lithium metal forms in situ during cycling. Pilot production samples have been delivered to select partners, with mass production targets around 2027. Chemistry direction has been publicly outlined. Every single one of these companies uses lithium. Every single one publishes at least partial chemistry direction. Every single one has extensive patent portfolios, and the ones closest to commercialization, WeLine at Mine 360 and Factorial at Mine 375, are backed by major institutional investment and validated by automotive OEMs. Donut Lab claims to have beaten all of them, with a chemistry they won't name, using materials they won't disclose, in a company that was founded 20 months ago, without a clearly visible patent footprint tied to the core battery chemistry. So let's bring it together. The marketing says 400 watt-hours per kilogram. The math says below 268. The forged lab report says 297. The authentic lab report says lower. The discharge curve says lithium-ion NMC. Every non-lithium chemistry in existence tops out well below 300. The supercapacitor theory is dead on arrival. And the simplest test that would resolve all of this, putting the cell on a scale, has been conspicuously, deliberately avoided.
Earlier this month, I reported on a little-known Finnish startup shocking the world when it claimed...
I want to be clear about something. I am not an electrochemist. I'm a person with a calculator, public test reports, and the ability to divide two numbers. Energy density is not a matter of opinion. It's not a matter of perspective. It's watts divided by grams. And right now, the watts and the grams don't agree. There is exactly one thing that would settle this instantly. An independent lab puts a healthy sealed Donut Lab cell on a calibrated scale. They run a full 1C discharge. They divide the total energy by the weight. And they publish the number. It would take one afternoon. It would cost a few $100s. And it would either vindicate Donut Lab completely or end the debate forever. The fact that this has not happened after 4 months and multiple VTT test reports tells you more than any press release ever could. The next video in this series examines the financial side. PwC, one of the world's biggest auditing firms, was hired to review Verge Motorcycles' books. They refused to sign off. What they found and what they couldn't find is the subject of that video. Subscribe and hit the bell so you don't miss it. And if you're a battery engineer, an electrochemist, or anyone with first-hand knowledge of the Donut Lab cell, I want to hear from you. Drop your analysis in the comments. If I'm wrong about the math, show me where